What's up, everybody? How you doing? Welcome to my latest video. A lot of you have been asking for me to do a quick video going over the M&M Candy Inference portfolio project, and I'm going to do that here for you right now. I think it's a nice idea because, to be honest, I've done this demo of how to do this with the class live a bunch of times, but with extenuating circumstances, some people maybe can't be here on class time, or maybe you're just one of those people that wants to see it broken down in a video so that when you go back and do the other steps, you can kind of jump in there and be like, all right, let me follow along with Mr. Richardson's video to do the next M&M. So here's an overview of how the project works. Mars Wrigley produces these little M&M bags, right? And they happen to say on their website how much is in these bags here, right? And what they're saying is on the website is like all of these, this is the amount of each of these that show up. So if you look for the blue, they're saying like 24% of the bag is going to be blue M&Ms, 20% of the bag is going to be orange M&Ms, 16% green, 14% yellow, and so on. And that's what Mars Wrigley, the company, is claiming on their website. However, I've opened a few of these bags, and it doesn't always work out to that. So what we're going to do is we're going to open a bag of M&Ms. And that's going to be our sample, our personal sample. And we're going to compare that to what the website says, those numbers I just went over. And we're going to decide, based on what's in this bag, is the website telling the truth? Are those ratios, those proportions, those percentages there correct? Or are the numbers in this bag so different that we can reject what the website says? And we're going to use a hypothesis test for that. So first thing that we should do is open a bag of M&Ms. So once we've opened this bag of M&Ms, we're going to want to count how many of each M&M showed up. Now remember what they said. They said something like, 24% of them are going to be blue. That's almost like a quarter of them. And you can clearly see by the bag I opened that not a quarter of them are blue. So we're going to do some comparison purposes and see what should happen, okay? First things first. They never told me how many should be blue, so let's figure that out, right? One thing that they did tell me was they told me at the beginning here that something like 24% of them were blue, right? Which I'll write as 0.24. And they also told me, if you read right here for the data displayed, that there's about 52 M&Ms in a typical bag. So if I multiply this by 52, this 24%, I can see that there's 12.48 expected blue M&Ms in the bag. That's how many they expect to be in there, is 12.48. Well, if I go back to counting what I got here, and I count the blue, you can see that there's only 11 blue ones there, right? So I'm going to write 11 here. Now, if you also count how many are in this bag, you can see that in the entire bag, I got 53 M&Ms, which was actually a little more than they said. They thought there'd be 52. So I got 11 out of 53, which I'm going to round to 3 decimal places. I'll take that 7 and round it up because of the 5. I got 0.208. So I got a little less than 21% blue M&Ms, and they told me it was going to be 24% blue. So the question I have to ask is this reasonable? If there actually was 24% blue M&Ms in this bag like they claim, is it reasonable to get a number like 20.8%, or is 20.8% low enough that I can reject what the website says and say, you know what, that number 24% is off? Well, that's what we're going to use statistics to find out. So I'm going to use this slide here with our fancy blue M&M person as our guide on how to do this, and I'm going to walk through it. First thing I want to do is just label some variables I'm going to use. I'm going to use a couple of different variables here. So let me label some of them. The first variable I'm going to use is P_W. That's going to be the ratio, or we'll say proportion, of blue M&Ms from the website, hence why I use the W, right? And I want to compare that, we'll say, to PS, which will be the proportion of blue M&Ms from our sample, all right? And we already know a lot of information about both of these, right? I already know that our sample, right? I got 11 out of 53 blue M&Ms, which was like 0.208 or like 20.8% of them were blue. And I already know what they told me about the website too, right? On the website when I went on, what they had told me was that it was going to be 12.48 out of 52, which was where that 0.24 came from. Now, if you're wondering, Mr. R, where did that 12.48 come from? Where did that 52 come from? I'll show you one more time. Back here, they said 24% of these were going to be blue, right? And they also said here that the bag contains 52. So I just wanted to figure out how many were blue. I just did 24% of 52 means that there should be 12.48 blue M&Ms. Let's say you wanted to know how many yellow M&Ms, right? You want to know how many yellow M&Ms, just take the ratio or proportion of yellow, which is 14%, multiply it by 52. They expect there to be like 7.28 yellow. So you just take the amount and multiply by the percentage to find what's in the bag. But back to the problem. I now have these two proportions, what the website says, 24% should be blue, and what my sample says, which is 20.8%. Now the whole idea, again, is to decide, is the website correct? Is there actually 24% blue M&Ms in the bag? And naturally, if I get 20.8%, that's normal, that should happen. That's a natural like fluctuation. Or is that 20.8% low enough that I can just say it's probably not 24% in the bag? Maybe it was 23%, 22, but it's just probably not 24%. So we write our null and alternative hypothesis. My null hypothesis is that assumption at the beginning, and I'm going to give Mars Wrigley, the producer, the benefit of the doubt, and I'm going to say that the two proportions are equal, right? So all this means is I assume at the start that the ratio of blue M&Ms, as stated on the website, is the same as what is in our bag, right? I'm just going to start. I'm going to give them the benefit of the doubt. Now, typically, we would write the alternative before we did our sample, but unfortunately, I already opened the bag of M&Ms. I know what the sample is, right? And what I can see what was happening was these things weren't equal. What I saw happen was that what was on the website was actually greater. So my alternative belief, what I'm going to try to prove is that the ratio of 24% from the website is actually greater, that there's less blue M&Ms in the bag than the website is saying. So that's what I'm going to say. So I'm going to try and prove that there is a higher proportion of M&Ms as stated on the website than actually appears in our bags. Great. So I just set the null and alternative hypothesis. Once I've set the alternative hypothesis that I want to prove and I can see that the alternative is greater than, I can decide which chart I want to use, which is for greater than. We learned in class that this is the chart here for not equal to, so I can say bye and not use that one. I go down, and this one is a wonderful chart. This is for greater than for the alternative, so I'm going to say keep it. And finally, the last one I'm also not going to use. This one is for less than, so that one I can say bye. Great. Got a lot of stuff going on now. Let's calculate degrees of freedom. Degrees of freedom for a two-sample test is just sample size plus sample size minus 2. If you recall, that's what those N stand for, N1 for the first sample, second sample. So this is actually pretty easy here. Our first sample size, if you recall, let's go back and look. The first one was out of 52. The second one was out of 53. 52 and 53. So here I'm going to write 52 for my first sample, 53 for the second sample. And if you're wondering what some of these variables stand for, there's a list at the bottom, and you can kind of look at those. Sorry, so much scrolling. There we go. 52 plus 53. This equals 103. Now, for degrees of freedom, all that does is it helps us find where on this chart we should be using. And I apologize, but the screen that's being recorded can't get as low as I would want it to get. But essentially, we're going to use the last row down here, which it's not really recording. And I don't think I have a way to kind of get it there. Oh, I can do this, maybe bring this up, scroll that down. Now you can see it, great. So you can see anything above 30, nice little bell, there we go. Anything above 30, you're going to use this, and our z-score is way above 30, it's like 102, so I'm going to use there. And if I go back and I read the initial problem on this slide, it tells you that we want to use a 5% significance level, so I'm going to go 0.05. And some people might say, I can't see any of that, Mr. R. I'm going to zoom in, and you can see the value I want is 1.64 should be fine for my z with the 5%, so 1.64. There we go. Great. So what does that mean? Well, that means that up here on our chart, we know what our critical value is. Our critical value is 1.64. Why was it 1.64? Well, we found our degrees of freedom from our sample size. We also found that we're going to be rejecting the top 5% of values because that's what it said in the initial problem, which means that we're going to keep the bottom 95% of values. So I'm going to put a 95% right here. Great. And this, of course, is the keep the null region. So here's how this works. Essentially, there's only two scenarios. We're going to find a z-score, a t-score, a z-score. And this 1.64 is the critical value. It separates where we keep and reject. So what we're going to do is if we get a value that's less than 1.64, we're going to keep the null hypothesis. And remember, the null hypothesis is that Mars-Wrigley is telling the truth. There's 24% blue M&Ms in a bag, and our sample didn't prove otherwise. However, if we get a value above 1.64, what that says is that Mars-Wrigley is wrong with their belief that there's 24% blue M&Ms in the bag, because what we got in our sample was extreme enough that it wouldn't be really reasonable for them to actually have 24% in the bag. Now the last thing to do is just figure out what the z-score is and decide whether to keep and reject. And if you're wondering where did that 5% came from, it came from right here. Use a 5% significance level. Great, great, great. Now what we need is the combined proportion. The combined proportion is really just like you're combining your two samples. So like you combine the two numerators and you combine the two denominators. That's all it is. It's like add the numerators, add the denominators. That's it. Like it's that simple. Add the numerators, add the denominators. So my first numerator was like 12.48 over 52. That was what the website says. And we got 11 over 53. Let's just double check those numbers. 12.48 over 52. Yeah, that looks solid. Okay. Now let's get an actual like decimal representation of this number, right? Let's get a decimal representation of this number. Now I'm just going to round it to the nearest thousandth. That 6 says round up. So I'm going to use 0.224 equals 0.224. Now what I'm going to do is I'm just going to plug into this formula, and I'll copy the whole formula so you can exactly see where I'm plugging into here. So I take this 0.224, and I'm going to plug it in everywhere there's a combined proportion P of C. So that's once, twice, 2, or 3. I'm not counting well today, 4. Great. N1 and N2, we know those are our sample size. Our first sample size was 52. Our second sample size was 53. And P1 and P2 are just our first and second proportion. I got fancy in this video and labeled them like PW and PS, but maybe I shouldn't have done that, and maybe I should have kept it simple for y'all and done like P1, and down here I could have done P2. Maybe I confused you. I hope I didn't, but that's P1 and P2. It's just these pieces down here. I hope I didn't confuse anybody with that. It's just this part here. These are P1 and P2. I just got fancy and said the sample was the second one and the website was the first one. And I hope I didn't confuse you, but I probably did. You can let me know in the comments section below. Which reminds me, make sure that if you're learning something right now and this is helping you, make sure you jam that like button. And if you haven't yet, make sure you subscribe for all the latest updates. So anyways, let's plug this in. We got P1 was what we got on the website. They told us that it should be 24% blue, and here we found that it was more like 0.208 in our sample. Well, great, let's find that t-score. plug this in, boom, I get 0.393. I'm not going to round it up because it follows by a 2. So our t-score is 0.393. At this point, there's no more mathing to do, no more calculation. It's time to just make a distinction as to whether to keep the null, meaning, yeah, the website's right, there's 24% in this bag, or it's likely that there's 24%, or the number that we got in our sample is so extreme that the website is wrong, and we can reject the belief that there's 24%. Let's take a look at this t-score of 0.393 and see where we fall on our chart. Well, I'm going to just write it down here for comparison, and we have to decide now, is 0.393, is that bigger than 1.64, larger, or is it less than? Well, hopefully you know that this number here is less than 1.64. It falls about here. It's like halfway between 0 and 1, about. What it means is that what we got in our sample is only 0.393 standard deviations above the mean, which isn't that far off. What it means is that if we actually had 24% M&Ms, like in the population of ratio of these M&M bags, that getting something like 20.8% is not that crazy. It's not crazy enough that I should reject the belief that 24% of the M&Ms are blue. So now I need to write some type of conclusion here, right? And I would say, based on our study, right, we want to keep the null hypothesis, which also means like fail to reject it, right? We believe that the actual proportion of blue M&Ms is, the blue M&Ms will say in a bag, blue M&Ms in a bag is likely 24%, like the website says. This is because our critical value of 0, or our z-score rather, or z-score, or you could say t-score, z-score of 0.393, was that it? Yeah. 0.393 fell below our critical value of 1.64. If there actually was 24% blue M&Ms in the bag, it would be quite reasonable to get a proportion such as 20.8%, like we got in a single sample. And there it is. So, yeah, did we get less blue M&Ms? Sure. Are we disappointed? Absolutely. Blue M&Ms are the best flavor, right? But does it mean that the website is wrong, that there's not 24%? No, we don't have enough proof of that. It's likely that there's actually 24% blue M&Ms in the bag, and we just got a number that was less than that. You know, not everything's going to be perfect. One M&M higher or lower just changes that, you know. So what you would do now is you would go back and finish the chart on slide 1, right? We only did one of them. We did the blue M&Ms. You would go forward and do the same for orange, green, yellow, red, and brown. When you go to do this, there's going to be a lot of similarities because the sample size is not changing. The sample size from the website, P1, is still 52. In our sample, there's still 53 M&Ms in the bag. So your N values aren't changing, but what's going to change is some of the proportions, your combined proportion. P1 will change because we're talking about a different color, or PW, right? All of these are different, 20%, 16%, and so on. And of course, your sample is going to change unless you happen to get 11 again when you count them up. I hope this video helped you out a lot on doing this. I enjoyed making it, so I hope you enjoyed watching it. Again, if you're vibing with this video and you learned something today, jam that like button. Just jam the like button, and also subscribe and leave a comment down in the comment section. I do look at these things. They do take a while to make, and it's nice to get some positive feedback from students that what I did was worth my time and that you enjoyed it. So until then, I'll see you on the next one. Thanks for watching until this point in the video. See you later. Bye, everybody.